Welcome to Tungal College online classes. Hello students, how are you all? Today I am going to start another important topic of atomic structure, but the name is shapes of atomic orbitals. In your previous classes, you learned about different types of atomic orbitals. What are they? They are s orbital, p orbital, d orbital, f orbital, and so on. So let us discuss shapes of these orbitals one by one in detail. First let us discuss shapes of s orbital. Let us write. First orbital is s orbital. Then how do we define the s orbital? So in your previous classes you learned about quantum numbers. There are different types of quantum numbers. They are principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So based on the azimuthal quantum number, we can define any orbital given on the board. The s orbital, p orbital, d orbital, and f orbital. So the permitted values for the azimuthal quantum number is denoted by the letter is L. The permitted values for the azimuthal quantum number, what we have learned, they are 0, 1, 2, 3, and so on. The minimum value for the azimuthal quantum number starts from the minimum value is 0. That means azimuthal quantum number starts from 0. It's clear. Then if L is equal to 0, we label the orbital as what? S orbital. If L is equal to 1, that orbital is what we labeled p orbital. If L is equal to 2, then that is d, and f orbital is L is equal to 3. By taking this point, we can define any orbital. First I will define s orbital. How do we define s orbital? Then you can try to define p orbital. Then s orbital is defined as an orbital with L is equal to 0. An orbital with L is equal to 0 is called as s orbital. And how do you define the p orbital? An orbital with L is equal to what? 1. An orbital with L is equal to 1 is called as p orbital. Then you got the definition for d orbital also. Then d orbital is defined as an orbital with L is equal to what? 3. An orbital with L is equal to 3 is called as d orbital. Similarly, we can define f orbital. So first let us write the definition for s orbital. How do you define an orbital with L is equal to 0 is called as s orbital. An orbital with L is equal to 0 is called s orbital. This is the definition of s orbital. Next, for L is equal to 0 for s orbital. L is equal to 0, what is the, based on the n values we can take the different types of s orbitals. N is the possible values is 1, 2, 3, 4, 5 and so on. These are the permitted values for principal quantum number. N is equal to 1, 2, 3, 4, 5 and so on. L is equal to 0, N is equal to 1. N is equal to 1, no, L is equal to 0. So this is 1 I am writing. L is equal to meaning is 0. That means I am writing as 1s orbital. N is equal to 2. L is equal to 0. That we can take as 2s orbital. So 1s. 1 is n value. This represents n value. This represents L value. So n value is 1, L value is 0, 1s orbital. N value is 2, L value is 0, 2s orbital. For 3s orbital, n value is 3, L value is equal to 0. Then 4, 0, that means 4s. 5, 0, that means 5s orbital and so on. They are different types of s orbitals. They are 1s, 2s, 3s, 4s, 5s and so on. We are writing on the basis of principal quantum number and azimuthal quantum number. These are the different types of orbitals. And the next point is s orbitals are spherical in shape or spherical shape. It is s orbital. It is spherical shape. Spherical shape. S orbital is spherical in shape. Then how to take this s orbital is a spherical in shape? I am taking one s orbital for understanding purpose. I am taking one s orbital and nucleus of an atom. This is the nucleus of an atom, and these are the electrons rotating. Imagine I took the orbit. Right, I am dividing this atom into 3 coordinates. So this is x coordinate, this is x coordinate, and this I am labeling as a z coordinate, and this is a y coordinate. So we are representing like this. Actually the coordinates are perpendicular to each other. This is x coordinate, this is a z coordinate. So both are perpendicular to each other. Previous class I said this is x coordinate, this is z coordinate, both are perpendicular to each other. So this is x, this is y. You can show like this. These two are perpendicular to each other. So all these coordinates are perpendicular to each other. We know this point very well clear. Now the point is from the nucleus, the probability of finding of electron at a given distance is same in all the directions for the s orbital. So the point meaning is if you go through anywhere around the nucleus, right, for s orbital the probability of finding electron at a given distance is same in all the directions. So based on this one, we can tell as the s orbital is spherical in shape. S orbital is spherical in shape. If you take the second 2s orbital, I'm drawing the 2s orbital here. First I'm drawing the 1s orbital, nucleus. This is 1s orbital. So this is 1s orbital, this is x coordinate, this is z coordinate, this is y coordinate. So I am drawing one more spherical structure like this region. So this is from a given distance, there is a probability of finding electron in the same in all the directions. This I am labeling as a 2s orbital. 2s orbital. This is a 1s orbital. This is 1s orbital. So between the 2s orbital and 1s orbital, here this place, this distance, this is there is an empty space is there. There is no probability of finding electron. So this region, what is the region I did not shaded? This region is called as a node. This region is called as a node. Node is defined as the region. This is the region around the nucleus. The region around the nucleus where the probability of finding electron is 0. So 0 probability of finding electron is there. That region is called as node. Here is maximum probability of finding electron is there. The dotted lines. This is thickness. What I shown here. This is the probability of finding electron is there. Between these two regions, this region there is no probability of finding electron. This region is called as a node. Node is defined as the region around the nucleus where the probability of finding electron is 0 is called as a node. Let us write the sentence. Node. The region around the nucleus, where around the nucleus in atom, where probability of finding electron, probability of finding electron is 0, is called node, is called in simple words 0 probability of finding electron in a particular region around the nucleus. That region is called as a node. Another important point of regarding the s orbital is we have different kinds of s orbital, 1s, 2s, 3s, 3p. The energy and shape of the energy and size of s orbital increases with increasing the n value. So I am taking the 1s orbital, 2s orbital. 2s orbital is big in size when compared to the 1s orbital. So n value is going to get increases, size and energy also is going to get increases. So simple point is size increases and size and energy. Size and energy of s orbital increases with increasing in the n value. So n value increases, then n meaning is principal quantum number 1, 2, 3, 4, 5 and so on. N value is more here, n value is less here. So 5s orbital has energy and size and energy is more when compared to the 4s orbital. 4s energy orbital size is more and compared to the 3s orbital. So n value is more, size is more, energy also will be more. The size and energy of s orbitals increases with increasing the n value. This is description regarding the s orbital. S orbital is defined as an orbital with L is equal to 0 is called as s orbital. The next one is it is a spherical in shape. There are different types of s orbitals. So they are 1s, 2s, 3s, 4s and so on. The next point is for s orbital size and energy is going to get increases with increasing the n value, nothing but principal quantum number value. Next we have p orbital. Let us discuss in details about p orbitals. P orbital. So how do you define the p orbital? Already I said orbitals are defining on the basis of azimuthal quantum number. The definition is an orbital with L is equal to 1 is called as a p orbital. Let us write the sentence. An orbital with L is equal to 1 is called p orbital. So this is the definition of p orbital. Then I am taking n values, azimuthal quantum number. N is equal to principal quantum number 2, 3, 4, 5 and so on. So L is equal to 1. So n is equal to 2, L is equal to 1. N is equal to, in the sense I am taking as 2, and L is equal to 1. 2, 1 in the sense I am writing as 2p orbital. And 3, 1, so 3p orbital. 4, 1, 4p orbital. 5, 1, 5p orbital. These are different p orbitals. Clear? So this 2 represents n value principal quantum number. This p represents, this L represents this p meaning is azimuthal quantum number. 2 is that means this number is a principal quantum number. This p represents azimuthal quantum number. L is equal to 1 value. Then the shape of the p orbital. P orbital is a dumbbell in shape. It has dumbbell shape. P orbital has a dumbbell shape. Then let us take the 3 different kinds of p orbitals for possible m value. So magnetic quantum number of p orbitals will be taken as base. Magnetic quantum number depends upon the principal azimuthal quantum number. So magnetic quantum number plus or minus L. So L is equal to how much we are taking? 1. And in the sense m is equal to plus or minus 1, that is equal to 3 possibilities, minus 1, 0, plus 1, minus 1, 0, plus 1. That means this p orbital splits into 3 different orbitals. Minus 1, 0, plus 1, there are 3 possibilities. Each p orbital has 3 possibilities. So they are one is px, py, pz. So mainly there are 3 orbitals. One is px orbital, py orbital and pz orbital. These 3 orbitals are oriented along the axis, so that p orbitals are directional in nature. Let us write the sentence. P orbitals oriented along the axis and hence they are directional. So what is the p orbitals? We can show here. I am taking 3 coordinates, right? This is x coordinate, and this I am labeling as z coordinate, and this is the y coordinate. So first I am showing px orbital. So along the axis, p orbitals are going along the axis. We have to show along the axis in the sense x axis, like this. So p orbitals oriented px, an orbital p orbital oriented along the x axis. We are labeling in the form of px orbital. So they are orienting in the along the x axis. And one more important point is each p orbital has 2 sections. This is one section and this is another section. These sections are called as lobes. Each p orbital has two sections, those sections are called as lobes. This is px orbital. Now let us write the py orbital. This is x coordinate, this is z, and this is the y coordinate. Then we have to draw two sections like this. So this is the shape of py orbital. Then we have is last one pz orbital. So this is x, this is the z, and this is the y. So we have to show pz orbital along the z axis, px orbital along the x axis, py orbital along the y axis, and pz orbital along the z axis. I already wrote the p orbital is oriented along the axis, so along the z axis. Even this one also has two lobes. So each p orbital has two sections. So these two sections are called as lobes. I labeled here. So this is px, py, and this is we have to label as pz orbital. So next point relating to it is size and energy of p orbital. So what are the different categories we have? 2p, 3p, 4p, and 5p. So size and energy, what is the point you learned here? Size and energy, here are the same point you have tried. Size and energy of p orbitals, size and energy of p orbitals increases with increase in principal quantum number. Increase in principal quantum number. That means n value. So n value increases, I wrote here, n value increases, size and energy is going to get increases. You may got a doubt why it is, so why the energy is going to get increases with increasing the principal quantum number. We have energy of atomic orbitals, there we will learn this point in detail based on n plus L value. I will make it clear in the topic. So this is p orbital. P orbital is L is equal to 1. P orbital is defined as an orbital with L is equal to 1 is called as p orbital. Next point is there are it has dumbbell in shape. Next point is p orbital oriented along the axis. We have the x axis, y axis, and z axis. If p orbital oriented x axis, we are calling as px, y direction in the sense py orbital, z direction in the sense pz orbital. And the next one is d orbital. Let us discuss about d orbital in detail. Then how do we define the d orbital? We will define the d orbital on the basis of azimuthal quantum number L. L is equal to how much for d orbital? 2. So based on this, how do you define? An orbital with L is equal to 2 is called as a d orbital. Let us write the definition. An orbital with L is equal to 2 is called d orbital. An orbital with L is equal to is called as a d orbital. This is the point number 1. Then L is equal to 2 you are taking, and what is n values we have taken? N is equal to 3, 4, 5, and so on. So n is equal to 3 I am taking, 3, L is equal to 2 in the sense you are taking d. So 3d orbital. Example for the d orbitals, 3d. Next we have is 4d, 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 and next one is 5d, and so on. So this is d orbital 1 point. The next one is for a given L value, there are 5 m values are possible. 5 m values possible for a given L value. There are 5 m values possible for L is equal to 2. If L is equal to 2, there are 5 m values are possible. What are they? So m is equal to, what is the formula? M is equal to plus or minus L. Magnetic quantum, m is nothing but a magnetic quantum number. Magnetic quantum number depends upon the azimuthal quantum number. So we can take as m is equal to plus or minus 2. Plus or minus in the sense we can take as first I am taking minus 2, minus I am taking applying minus 2, minus 1, 0. Next one is plus 1 and plus 2. So total minus 2, minus 1, 0, plus 1, plus 2. Total possibilities how many will be there? 5 possibilities. So there are 5 m values are possible for given L value. This point indicates that there are 5 d orbitals. There are 5 d orbitals. They are designated as, there are 5 d orbitals. Very important points. The 5 d orbitals and designated as dxy, one orbital. Total 5 we have take. One is dxy, the second one is dyz, third one is dxz, fourth one is dx square y square, and the last one is dz square. So for given L value, there are 5 ml is possible, -2, -1, 0, +1, +2. So this indicates that 5 d orbitals are possible. They are dxy, dyz, dxz, dx square, y square, and dz square. So regarding this, another point, important point is shapes. dxy, dyz, dxz, dx square, y square, all they are double dumbbell. Double dumbbell shape. Only dz square orbital is a dumbbell shape. Dumbbell shape, clear. And another important point, while drawing the structures, we have to draw the structures of these d orbitals. While drawing the structures, dxy, dyz, and dxz. These three cases, lobes present lying between the axis, dx square, y square, and dz square, lobes lying on the axis. What is the point is, dxy, dyz, dxz, xz, zx. These three cases, lobes lying between the axis. Lobes lying between the axis. In the case of dx square, y square, and dz square. So lobes, in these two cases, lobes present are lying on the axis. Lobes lying between the axis, lobes lying on the axis, you will understand by drawing the shapes of these orbitals. First I am taking dxy orbital. Dxy I am taking. So we have to take 2 coordinates. I am taking 2 coordinates, x coordinate, and this is x axis, this is y axis. So for dxy, the lobes we have to show lying between the axis. So this is y axis, this is x axis. So between these two axes we have to show the lobes, and another lobe like this. So this is the shape of dxy orbital. Next, shape of dyz orbital. This is dxy orbital. Next one is dyz. So yz in sense, what is the coordinate axis? We have to take axis. So we have to take, one is y axis, we have to take another one is z. I am labeling here is y axis, I am labeling it z axis. Then they are also present between the axes. Clear? And one more common doubt you have to, both structures look like same. But what is the common difference? Here I took x and y here I took y and z. So meaning will be the same because all the 3 coordinates are perpendicular to each other. Then we have next one more is there, that is dxz. xz. That means this axis we have take x axis. This one is what we have take y axis. Sorry, this is z axis. xz. Then what is the shape? We can write like this. So this is dxy, dyz, and dxz orbital shapes. Next remaining we have is dx square, y square, and dz square orbital. So if you write the structures, this is dx square, y square. So this something. In this case of dx square, y square, these are the axes. X axis we are taking, this is y axis I am taking, we have to show the lobes on the axis, not between. Here is between the axis, but we have to show on the axis like this. So this is the shape of dx square and y square orbital. The last one we have is dz square. This x I am taking, this I am taking is z. Dx square, dz square orbital. Only one orbital we have, only one axis we have to take. These two total lobes will be present on the z axis itself. So these are the lobes, and another I am drawing like this. This is the dz square orbital. The z square orbital. So one common difference is dxy, dyz, dxz lobes are lying between the axis, and remaining two cases dx square, y square and dz square the lobes are lying on the axis. And there are total 5 d orbitals are possible. They are dxy, dyz, xz, dxy, yz, xz, dx square, y square, dz square. On basis of your telling 5 d orbitals are possible on the basis of magnetic quantum number. For given L value, L is equal to 5 magnetic 5 m values are possible. They are -2, -1, 0, +1, +2. So based on this point, we are writing 5 d orbitals. So this is d orbitals. Next topic is energy of orbitals. Energy of orbital depends upon the two quantum numbers. One is principal quantum number and the second one is azimuthal quantum number. In simple words, energy of orbital depends upon the n value and L value. So we are discussing energy of orbitals in two different cases. One is hydrogen, the second one is multi-electron atom. So hydrogen has only one electron, we are taking it as a one case. The second case is multi-electron atoms, remaining all elements, they contain more than one electron. So two different cases we are taking. The first one we will discuss about hydrogen. So the different possible orbitals we will write. So possible orbitals is 1s orbital, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f and so on. So 4s, 4p, 4d, 4f and so on. So these are the different possibilities of orbitals. 1s orbital, 2s orbital, 2p, 3s, 3p and so on. So what is the point we have to write is energy increases by increasing n value. So n value increases, the energy is going to get increases. This point to keep in mind. N is nothing but what? Principal quantum number. N is nothing but principal quantum number. So principal quantum number value increases, the energy of orbital is going to get increases. Now we have to take it. Then 1s orbital, 2s, 2p. So one more important point is n value is same, energy will be the same for hydrogen like species, hydrogen. So n is same, energy is same. 1s orbital, 2s, 2p. 2s, 2p, n value is same. This is nothing but what? N value. N value is same, their energies are same. N value is same, energy is same. If you have to compare these two, 2s, 2p, 1s, n value is more for 2s when compared to 1s, so 2s energy is more than that of 1s orbital. 2s, 2p energy is greater than 1s orbital because n value increases, energy is increases, n value will be the same, energy will be the same. They are calling as degenerate orbital. The orbitals with the same energy is called as degenerate orbital. You will write the sentence. The orbitals with the same energy is called degenerate. Is called as degenerate orbitals. This is the thing. Next one is continuation. 3s, 3p, 3d. 3s, 3p, 3d, n value 3, 3 and 3. N value remains same for these three cases. N is same in the sense, energy is same we can take. Then compare this set with this. Then 3 is greater value when compared to that 2, so that its energy is greater than the 2s, 2p. 3s, 3p, 3d energy is greater than 2s, 2p. 3s, 3p, 3d have same energies. Then 4s, 4p, 4d, 4f. n values for all the cases 4 is there, so 4s 4p all energies will be the same. So these orbitals are called as degenerate orbitals because they have same energy. But compare this rate with this one, 3p 3d, 3s 3p 3d, this is 4, n value is increases, so energy of 4s is greater than 4p is greater than 4d is greater than 4f. Now we got one more doubt. What is the doubt is, sir, hydrogen has only one electron, how this many number of energy levels is possible? Now for this answer is, I am taking an atom, its nucleus, in the hydrogen only electron present in the ground state here, but we are taking this many number of energy levels. Why do we taking all these energy levels? Ground state, so this only one possibility, 1s orbital. This is second energy level, possibility is 2s and 2p is possible. This is 3s 3p and 3d possibility is there. This is 4s 4p 4d and 4f. This is n is equal to 1, n is equal to 3, 4, n is equal to 1, 1s, n is equal to 2s, 2p, n is equal to 3, 3s, 3p, 3d, n is equal to 4, 4s, 4p, 4d, 4f. These are the possibilities. Now electron present in the ground state, electron present in this one, first energy state we are calling as, this is ground state for hydrogen. Ground state for hydrogen. If electrons get excited to the higher energy levels, electron will be jumped to the higher energy levels, then that case we have to consider these energy levels. Otherwise in hydrogen, electron present only in the one first orbit. If energy is taken by that hydrogen, electron will be jumped to higher energy state. In such case we have to consider all these orbitals. That is the conclusion. So what is the point is, the energy values of orbitals, energy of orbitals in hydrogen depends upon the n value, n will be increases, energy is going to get increases. The orbitals with the same energy is called as a degenerate orbitals. This is a hydrogen. Next one is the energy of electron in multi-electron atom. Energy of electron in multi-electron atom. In the case of multi-electron atoms, the energy of electron depends upon the principal quantum number and azimuthal quantum number. The energy of electron or orbitals also you can take. Electron in is depends on principal quantum number and azimuthal quantum number. Azimuthal quantum number. So depends upon, this is L value, principal quantum number in the sense L value. In simple words, the energy of electron depends upon the principal quantum number n value and azimuthal quantum number L value, n plus L value decides the energy. Now I am taking orbitals, I am taking n value or value of n. Next we are taking a value of L. Next we have n plus L value, n plus L value. Right, I am taking first 1s orbital, 2s orbital, 2p orbital, 3s, 3p, 3d, 4s, 4p, 4d. So different orbitals I took here. So what are the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. Let us look into the which orbital is higher energy, which orbital is lower in energy. First I am taking 1s orbital. 1s orbital, its energy is n value is, first number is this number is the principal quantum number, s, p, d, their n values are already p plus L and L is equal to 0, that will be taken as s orbital, L is equal to 1, p orbital, L is equal to d orbital and so on. So n is equal to what? 1. For this case L is equal to 0 in the sense what we can take, s orbital, L is equal to what? 0 value. So n plus L value, 1 plus 0, that is equal to 1. Clear? For this case n is equal to 2, L is equal to how much? S orbital again 0. So 2 plus 0, that is equal, n plus value is 2. Then this case 2p orbital, n is equal to remains same 2. L value is p orbital. P orbital L is equal to what? 1. That is equal to 2 plus 1, that is equal to 3, isn't it? Next to 3s orbital, 3, n is equal to 3, s is equal to 0. So 3 plus 0, n plus is equal to again 3. Then 3p orbital, this is 3. P orbital L value is 1, that is equal to 3 plus 1, that is equal to 4. Next 3d, 3. D orbital, for d orbital L is equal to what? 2. So this is 2, that is equal to 3 plus 2, that is equal to 5, isn't it? 4s orbital, 4. L is equal to 0, that means 4 plus 0 remains 4. Then 4p, 4, p is 1, that is equal to 4 plus 1, that is equal to 5. Next 4d, 4, this is what? 2. 4 plus 2, that is equal to 6. So we got n plus L value. Based on the N plus value, we have to arrange orbitals into energy increasing or decreasing order of their energy level, energy order. So one important point, the orbitals with lower n value, its energy is lower. First point, the orbital with lower n value, the orbital with lower n plus L value, the orbital with lower n plus L value, good, keep in mind, lower n plus value, its energy is lower. And its energy is less. Point number 1. Point number 2, based on these 2 points only, I am giving 2 points. Based on these 2 points only, we can arrange the orbitals in increasing order, decreasing order of their energies. If n plus L value is same for 2 orbitals. If n plus L value is same for the 2 orbitals, in such case the orbitals with lower energy has the orbital with n value is lower has a lower in energy. If n plus L value is same for the 2 orbitals, the orbital with lower n value, the orbital with lower n value has lower energy. The orbital with lower n value have a lower in energy. N value is less, energy will be less. N value is more, n value is more, energy is more. When n plus L value will be the same in such case. Let us arrange all this. So n plus L value 1, 2, 3, 3, 4, 5, 4. So among all the cases, the n plus L value is small. So lower than value, the orbital with lower n plus L value, lower energy. That means 1s energy is less than. 1s orbital energy is less than. Then 2 remaining, there is no 2. So 1s energy is less than 2s orbital. 1s is less than 2s orbital. Is less than. Next 3 we have to check. 3 will be there. Both the cases n plus L value is the same. 3 and 3. So what is the sentence when n plus L value is same? If n plus L value is same, the 2 orbitals, the orbital with lower n value. So which has the lower n value, that we have taken. So 3, both are same. Here n value is 3. Here n value is 2. Lower n value has the lower energy. That means lower n value is 2p is lower n value and 3s is higher n value. That means 2p is less than 3s. What my point is, these 2 cases n plus L is equal to 3. Value is same. In such case, the orbitals with lower n value is lower energy. Here n is equal to, here is 3, n is equal to, here is 2. Lower n value is lower in energy. So 2p is less than 3s. Next, here 4 is there, here 4 is there. This is what 3p, and this one is what we have is 4s, 3p and 4s. In the case of 3p and 4s, n value is 3p, 4s, both have same n value, that is equal to 4. N plus L value is same. In such case, which is the lower n value? Here is 4, n is the 4, here n is the 3. So this is the lower, that means less than 3p is less than 4s. Next, 5 and 5, these two orbitals. 5 and 5, 5 in the sense what? Which one? 3d. 3d and 4p. 3d and 4p has the same n value, n plus L value. What is that value? N is equal to 5. 3d and 4p have same n plus L value 5, 5. So which is the more energy or which is less energy? Less n value. Here 4p, here 3d. 3 is the less value. So that 3d is less than 4p. Is less than remaining only one half, that is equal to 4d. So this is 4d. So we are writing the energies of orbitals or energy of electron on the basis of n plus L values. So these are the energies of orbitals. The final conclusion is the energy of these various orbitals is 1s is less than 2s is less than 2p is less than 3s, 3p, 4s, 3d, 4p and 4d and so on. So energy of orbitals. So conclusion is energy of electrons or orbitals in the hydrogen atom depends upon the only n value. In the case of energy of electrons in the multi-electron atom depends upon the n plus L value. N plus L value is lower, the orbital energy is lower, energy of electrons is lower. N plus L value is more, energy is more. If two orbitals have same n plus L value, in such case the orbitals with lower n value has a lower in energy. So these 2 points we are able to keep in mind. Then we will be able to get we are able to write energy order for any orbitals. So this is today's topic. So next class will come out with another atomic structure topic.